All right, we're going to talk about exponential growth and decay a little more. We're going to do a few examples, and we're going to use Alex for those examples. Just as a quick recap, though, exponential growth and decay, it's a special case of an exponential function. This is the basic formula for all exponential functions, where a is the initial amount, b is a constant amount of growth or decay, and then x is the variable. It is considered a growth, an exponential growth, if b is greater than 1, because your numbers will get bigger and your graph will start looking like that. It's considered an exponential decay if b is less than 1, because it'll start giving you smaller numbers. Now in Alex, the homework goes through the exercise of you comparing, first off, in number 1, comparing what the functions will look like. Notice that this function is not exponential because there is an exponent of 2, but the variable is not in the exponent. So this is just a quadratic, turns out. This one has an x in the exponent, so that makes this exponential. So by plugging these values in, you'll be able to make a comparison between the two. I'll let you do that on your own, just as a discovery piece. Similarly, numbers 2 and 3 give you some information. So you have some graphs here, a few graphs, and some data points. Asking you to decide whether or not, which of these figures have the best fit, in this case, figure 3. And then if you wanted to plug this in, in order for you to go through and do this, after 31 years, you would put in, instead of x, 31, and do the math on that. Now, it may not let me move forward because I've done that. So I'm just going to plug something in here. This is not the case, but to the nearest hundredth. 0.80. I'm making this up. That is not the correct answer. I just guessed on that. I don't want to recheck it. I just want to move on to the next problem. Same thing for number 3. So you'll be able to go through and do that. I'm going to focus more on numbers 4, 5, and 6. They're all the same, but let me take a look here. If I read this, it says that to begin a bacteria study, a petri dish had 2,100 bacteria cells. Each hour since, the number of cells increased 7.4%. Let T be the number of hours since the start of the study. Let Y be the number of bacteria cells. I want to write an exponential function showing the relationship between Y and T. So the key here is that it's had a starting point and then it increased by 7.4%. So for this example, for number 4, I see that my initial amount, A, will be 2,100. That's what I started with. And then my B is going to be greater than 1 because it is increasing. It's a growth. And in fact, I'll have 1 point. Well, if it's increasing by 7.4%, just make sure we know that 7.4% is equal to 0.074. You move it 2 places to the left, 1, 2. So not only do I have just this whole 1, I'm increasing it. I would just add this 0.074 over here. Let me erase that and write that a little bit better. Since I know it's increasing 7.4%, let me put that as a decimal. That's really going to give me 1.074. It's one whole one plus this 7.4%. So this is my B, this is my A. And so if I were to write the function, my A is 2,100. My B, and I'll put this in parentheses, 1.074, and that's going to be raised to the x power. Now, we're not talking about x and f of x here. We're talking about t for time and y being the actual output. So instead of f of x, I'm going to write y. The numbers will stay the same, but instead of x, I'm going to use t. So that's what I'm going to write over here. I'm going to say that y is equal, y is equal to 2,100 times 1.074 to the t. And that should be good unless I did something small. So we're good. So it's really just paying attention to that. If we look at another one with 10 seconds left, we would actually decade. We would do 1 minus 0.0678, whatever that number is, and it'll go right here. Okay.